Welcome to this lecture on Antipodal points with same temperature, an application of location of roots theorem by Dr. Rajesh Singh.
Hello everyone. So today we are going to discuss a remarkable fact about our earth and its temperature. So did you know that there are always 2 points on opposite sides of the equator of the earth with the exact same temperature? So there are always 2 points on the opposite sides of the equator of the earth with exactly same temperature, and we can prove this fact mathematically. So let us see how we can do that. So for that, let me first, so this is our earth and this is our sun and this is our equator. So now we are going to represent this equator by a circle. So let me just draw a circle for you all. So suppose this is our earth, and now let me draw a small sun. Okay, so this is our sun, and let me so this is our earth, and let us take a center point for this. So for that, let me, so we can mark this as the center of the earth, so let us call it O. Fact is that there will exist 2 points, so this circle is representing the equator of the earth. So this circle represents the equator of the earth. Now, so what this fact is that there will exist 2 points A and B. So there will exist 2 points. So like this, if you see this, the sun is facing like this. So there will exist some 2 points. So call it, let us call it A. So there will exist some point A and a directly opposite point that passes through the center B. So these are antipodal points. They are directly opposite to each other, and the line joining them passes through the center of the earth and the center of the equator also. So what this fact is that there will exist 2 points A and B such that temperature at the point A is equal to temperature at the point B. So there will be 2 points such that temperature at those points will be exactly equal. Now how we are going to prove this mathematically? So we have to somehow represent this problem mathematically. So we are going to use our location of roots theorem to prove this fact. So to use location of roots theorem, we need some function. So for that, let me first just mark, so let me just draw an initial line. So this is a reference line. So I will be just explaining you why I need this reference line. So this is our initial line or reference line, initial line or a reference line. So what is importance of this is that this is a, if I take any point on the equator of this, on this equator, then we know that in fact any point on a circle can be represented by the angle that the line joining the center and that point makes with this initial line, right? So if I have any point, say any arbitrary point P which lies on this equator of the earth, then I can represent this point P by the angle which this line OP makes with the OX, right? This line makes, so now I can represent this point P. I can uniquely represent this point P by the angle theta, where the theta is the angle. So theta is the angle that OP makes with the OX. Okay, so TP is equal to, oh sorry, the point P is represented by T theta, that which T theta, and we call it T theta because this is the temperature. This represents temperature at point P. So we are representing the temperature at point P by T theta. Okay, so T theta represents the temperature at point P. So any point temperature at any point of this curve can be on this equator of this can be taken in terms of theta, where theta is the angle that point, that the line joining the center of the equator, and that point makes with the OX in anti-clockwise sense. Okay, so for example, if I have this line, so let us take a point Q which is directly opposite to P. So let me take a point Q which is directly opposite to, okay, so this line, this point Q is directly opposite to, so this point Q is directly opposite to, so what is the so temperature at Q is, so temperature at Q can be written as temperature at point Q is T theta plus pi, because this is theta plus pi, this angle is theta plus pi. If you look at this angle, so it is theta plus pi. So if there are 2 points which are directly opposite to each other, then their temperature can be written as T theta and T theta plus pi. Since now what is the temperature at this x point? Temperature at x is T0. Okay, so let me just represent the temperature at x is, it is T0, and T0 is also equal to T2 pi, because this will also make an angle 2 pi. When we will go all around this, then we will get that T0 is equal to T2 pi. So now, because the sun rays distributes evenly on the surface of the earth, so the temperature is distributed evenly, temperature varies along the equator of the earth evenly. Now this side of the this side, so this side of the earth is facing the sun directly, so this will be warmer side, right, and this will be colder. So at any point, at any given time, the temperature of the earth varies across the along the equator, it varies along the equator. So at this point it should be maximum, because this is facing the sun directly, then it will, at this point there will be slightly less, and similarly all these points. So we can assume that the temperature along the equator of the earth varies continuously. So we are assuming that the temperature across the curve varies, across the equator of the earth varies continuously. So now we can define a temperature function which can represent the temperature at each point of the equator. So we will define a temperature function. So let us define that. So T, and this should be from, because this angle, every point can be represented by an angle from 0 to 2 pi, so this, its domain should be 0 to 2 pi, and codomain we can take it as r, and so T basically takes theta to T theta, temperature at any point. Okay, so this is the function temperature. So this represents the temperature at the point which, at the point P, which makes an angle theta with the initial line. So okay, so temperature corresponding to theta. So we have defined the temperature function clearly by our assumption that temperature is varying continuously along the equator of the earth. So by our assumption that temperature is varying continuously on earth, T is continuous function on 0 to 2 pi. So we have got a continuous function. Also T of 0 is equal to T of 2 pi. So it is somewhat periodic, because again it will go on like this. So T of 0 is equal to 2 pi, because this line represents both 0 as well as 2 pi. So T of 0 is equal to T of 2 pi. We are measuring this angle in anti-clockwise direction, right? We are measuring this angle in anti-clockwise direction. So now we have the complete setup. Now what we want is, let us draw this model of the earth again. so that we can have more clarity. So let me just draw. So again take it as center, then initial line. Now what we want is that if you see that if there is some point A1, suppose this is A1, this point is A1, and let me draw a totally opposite point. So if you look at this, okay, also let us draw our sun so that we have the reference. So this is our sun, so this is facing, so we have taken it so that it is facing the sun directly. So this is our O, this is our X, this is A1, this is B1. So B1 is opposite point of A1, and let us take another point. So now, so T of A1 is definitely greater than T of B1, right? Because this side is facing the sun and this side is slightly on the opposite side of sun. So T of temperature at point A1 is greater than temperature at point B1. Similarly, if I take this point A2, if I move this point a little bit and come to A2, then so let me just, or so then if, so let me take the opposite point of this. So this is our B2. So this is our B2. So clearly now B2 is facing this sun directly. So temperature at A2 is less than temperature at B2. So what is happening is that if you take the difference temperature at A1 minus temperature at B1, so these are opposite points. So we are taking the difference at all the opposite points. We are taking the difference like this. We are taking all the points, all the different points like this. We keep on taking points like this. So we keep on moving like this. Okay. So we keep on moving like this. We keep on moving like this. We keep on moving like this, and at each point we take the difference of the temperature of the opposite point. So at this point temperature is greater than 0, while at A2 the T of A1 A2 minus T of B2 is less than 0. So you can see that the difference between the temperatures at the opposite points is moving from positive to negative as we move away from this initial line. As we move away from the initial line in anti-clockwise direction, then we see that the temperature is the difference between the temperature at the opposite points are changing from positive to negative. So now because our temperature is a continuous function, so their difference is also a continuous function, and since the difference is continuous and it is changing its sign from positive to negative, so it must cross 0 at some point. So that is the idea behind this proof that we are going to write. So now we have to define the difference function. So we will define h from 0 to pi, because we are taking opposite points together, so that's why we have reduced this interval to half of the original interval domain. So h from 0 to pi to r defined as h of theta is equal to, so we will take t theta minus t theta plus pi. So we are taking the difference of the temperature at opposite points along the equator. So this is the function h. This represents the change or difference in the temperature at opposite points along the equator of the earth. So for all theta belonging to 0 to pi, then as h is t is continuous, as t is continuous on 0 to pi, 0 to 2 pi, so this by algebra of continuous function, our h is continuous on 0 to pi. Now our h is continuous on 0 to pi. Now what about this point h0? H0, so this is h0, this will be totally opposite this, right? Its opposite point is, so this you can take the opposite point of this. So this is the opposite point, say y. So y is opposite of this and its angle is theta. So h0 is equal to t0 minus t pi, right? So clearly t0 it is facing sun, so it has to be greater than t pi. If it is not equal to t pi, then it has to be greater than t pi. Now h is continuous on 0 to pi. What about h of 0? H of 0 is t of 0 plus no, minus t of 0 pi, minus t of 0 plus pi, so which is equal to t0 minus t pi. H of pi is equal to t pi minus t of pi plus pi, which is t pi minus t2 pi, and because t2 pi is equal to t0, we have observed this fact here that t0 is equal to t2 pi, both the points are same. So h0 and h pi is equal, so h0 is equal to minus of h pi. Now if t0 is equal to t pi, if it is equal, then we have two opposite points, then we have two opposite points at which temperatures are exactly same, right? Because here at 0 and pi there are antipodal points, and at them temperature is exactly the same. Temperature is exactly the same. If t0 is not equal to t pi, then h0 and h pi have opposite signs. One is positive and one is negative, because one is t0 minus t pi and another is t pi minus t0, so they have opposite signs. So by location, and since h is continuous function, so by location of Fruit's theorem, since h is continuous function and they have opposite sign at these 2 points, so by location of Fruit's theorem, there exists c lying between 0 and pi, c belonging to 0 to pi, such that h of c is equal to 0. So this implies Tc is equal to Tc plus theta. So we have got a point at which the temperature, we got two opposite points, C and C plus theta represents the antipodal points, and at which the temperature is are equal. So hence there always exist two antipodal points on the equator of the earth, with exactly the same temperature. So what we have basically done is that we have represented the temperature at each point of the curve by a function t, and because the temperature varies uniformly or continuously over the equator, so t is a continuous function by our assumption, and also because this point, initial point, this initial line, reference line, it that t0 is equal to 2 pi, because this is the same for 0 as well as 2 pi. So t0 is equal to 2 pi, so we have this condition that t0 is equal to 2 pi. So we define another function h, which is basically which gives the difference between the temperature at the antipodal points. It gives the difference between the temperature at the antipodal points. So here also we can see that temperature is changing from positive to negative, so we know that we will attain 0 at some point, that is there must exist some point at which the temperature are exactly the same. So that's why, so for that we define this function h, and now using the continuity, this function h is also continuous, and also it is having different signs at 0 and pi. Either they are equal, and if they are equal then we have that 0 and pi are the two antipodal points. If they are not equal, then we have h0 equal to the sign of h0 is different from the sign of h pi, so they have opposite signs. So by location of roots theorem, there will exist some point at which the difference is 0, that is there exist 2 points, two antipodal points at which temperature is exactly the same. So there always exist two antipodal points on the equator of the earth with exactly the same temperature. So this completes the proof of this interesting and simple fact that there exist two antipodal points on the equator of the earth with exact same temperature, and this is a very simple application of location of roots theorem. So we see that the mathematics can be applied in very unexpected way. So we are able to prove this very interesting fact using our simple location of roots theorem. So this much is there in this video. Thank you everyone. Have a good day.
Thank you for watching this video. Please subscribe to our YouTube channel, Online Learning, to stay updated and share with your friends. Happy learning through online learning. To watch more, click on any of these cards. Thank you once again.